Hey everybody, welcome back to the Introductory Astronomy Lab. This is going to be our fourth lab, and in this lab we're going to focus on Kepler's laws. Now, just real fast, give you a background on Johannes Kepler. He was a German high school teacher, actually, who was very gifted mathematically. And he went on to work with an astronomer, Tycho Brahe, who had done extensive observations of the orbit of Mars around the Sun. And what Kepler did is he took those observations and he created essentially, well, what he's most known for are his three laws. And what is extremely interesting about these is that these laws, while they kind of allude to Newton's laws, the laws that we studied last week, they predated Newton's laws. So Kepler kind of came up with these before Newton was even born. All right, so his three laws are pretty simple, but they're very powerful in how they allow us to talk about astronomy. So the first law that Kepler developed was that planets, when they orbit another body, orbit in an elliptical orbit. All right, so if you have the Earth going around the Sun, it's going to go in a more elliptical orbit as it travels around the Sun. Not really circular. For centuries, they had assumed that it was, not only was it geocentric, meaning the Earth was at the center, but that the orbit was perfectly circular. And Kepler showed through analyzing the observations of the orbit of Mars that that wasn't the case. By using elliptical orbits, Kepler was able to show that his model more accurately reproduced the orbit of Mars around the Sun than using the epicycles that had been used up to that point. All right, now because we're talking about ellipses, let's go over just some basic properties of ellipses. So I'm going to go ahead and draw an ellipse. All right, and well, let's start out with a circle actually. So we all know in a circle that you have a center, and the distance to the outside of the circle is the radius, and the distance across is the diameter. All right? An ellipse is kind of similar, but different. An ellipse sort of looks like an elongated circle. So what we're going to do is we're going to draw ourselves an elongated circle or an ellipse. Well, let's try that again. All right, there we go. Now, every ellipse has two foci. All right, and they're what helps define the shape of the ellipse. In fact, how close together these foci are or far apart determines how actually circular the ellipse is. If both foci basically coincide with one another, you end up with a circle of it. There's also two axes that are important. There's the major axis that goes along the longest part of the ellipse, and there's the minor axis that goes along the shorter section of the ellipse. Also, half of each axis has a name as well. Half of the minor axis is the semi-minor axis, and half of the major axis is the semi-major axis. And what Kepler found is that the motion of the Earth around the Sun, if you were to accurately draw it, like this, draw our ellipse again. All right, it's not exact, it's close enough. The Sun is actually located at one of the foci, and the Earth kind of travels around the Sun in an elliptical pattern. So that's Kepler's first law. The second law that Kepler discovered was that as a planet travels around its star, or any celestial body, it's going to, for every length of time, it's going to map out an equal amount of area. So what does that mean exactly? So let's erase the Earth real fast right here. So let's say we have the Earth moves from here to here in 1 month. Okay? If you were to connect from the center of the Sun to each of these positions just like that, the Earth would have swept out this area right here. Yes, we're all in there. All right? Now, the Earth is moving slower when it's further away from the sun and faster when it's closer to the sun. So in the same amount of time, if we say the Earth was here and here, the Earth will have swept out this area when it's moving a little faster, but area 2 and area 1 will equal one another. Alright? And this law is actually very neat because the reason why this is that the Earth will sweep out an equal area in the same amount of time is actually a result of the conservation of angular momentum, which wouldn't be developed for at least 100 years later. So that allowed us to, not only did the elliptical orbits allow us to model the planets' orbit around the sun or any celestial body around another more accurately, it also allowed us to analyze the speed and the motion of the planets more accurately. And the final law is called the period radius law. It's another very powerful law that Kepler came up with. And the reason why is that it's applicable to any celestial body. And basically what it says is that the period of rotation squared is equal to the radius cubed. Now, this is the average period and the average radius. So, if we go back to the solar system real fast, you have your elliptical orbit, the sun at one of the foci, and the Earth going around. The period, which is the time it takes for the Earth to go around the sun once, squared is equal to the average radius, or the average distance that the Earth is from the sun. And what this allows us to do is that no matter how far a planet is away from us, or how far away another celestial body is, if we can get the period of its rotation around another body, we can find the radius. All right? The period has to be in years for this equation to work, and the radius has to be in astronomical units. So let's say, just as an example, let's say that the average period of Jupiter is, and this is just, I'm just making this up as we go along, is 3 years, even though it's not, it's longer. All right? And we wanted to find the average radius. We would just plug it in there, we get 9 is equal to r cubed. And the average radius of that planet, whatever it's called, is the cube root of 9. All right? So those are Kepler's laws. They're very important as far as astronomy is concerned. It's kind of the bedrock of observational astronomy, being able to calculate and describe planetary motion this way. Provided a lot of evidence for the heliocentric model that later scientists, specifically Galileo, would use in order to show that the heliocentric model was the correct model of the solar system. And they're very powerful equations. Now, in our lab this week, we're going to be actually recreating an elliptical orbit. And what you're going to do, and we'll go over it later in the video, is essentially you're going to create your own ellipse, just like that, using 2 pins, and then you're going to chart the motion of a hypothetical planet around that ellipse. And what you're going to do is you're going to show that your hypothetical planet, as it travels around your star, that given a set amount of time, it'll map out equal areas. And you'll essentially prove Kepler's second law. All right, guys, so I'll see you at the lab demonstration, which is coming up in a few seconds. All right, everybody, so now we are on to the practical part of our lab. For this one, what you're going to need are your pins, the string, graph paper, and I have some cardboard to put on the back so that the pins don't go through the graph paper and into whatever you're working on. So I already set up my 2 foci, or my foci. All right, and what you're going to do is you're going to take your string, tie it into a loop, and put it around the pin pins, just like that. Then basically what you're going to do, you're going to take the string, make sure it's taut, and trace out an ellipse all the way around. Just go all the way around. All right, just like that. When you're done, remove the string, take out the pins, and now time to go to work. All right, so the first thing we want to do is we want to map out our first sector. So let's call it sector 1. All right, I'm going to pick just straight across from one focus to the edge of the ellipse, and I'm going to say, this looks good. We'll pick right here on the ellipse. So I'm going to get my ruler out. We're going to draw a line right to there, just like that. Okay. Now what we want to do is we want to use our area of a triangle equation, 1/2 base times height, to calculate the area that is approximately in here, or the number of blocks. Beforehand, I counted out that this is 15 blocks right here and 6 blocks right there. Once we calculate this area, we're going to go over here and we're going to count out the area. And when we're done counting out our blocks, we're going to draw another line, and this will show that basically as the planet rotates around, or the comet in this case rotates around the star, that because it's slower here and faster here, that given the same time, it'll map out equal areas. All right, so we know this side is 15 blocks, and now we just have to get the base. So this would be our height, and this would be our base. Now this is an approximation, it's not exact, but it is close enough. So 1, 2, 3, 4, and 5. So area is equal to 1/2 5 times 15. The area is equal to about 7.5 times 5, which is about 37.5 blocks of area. All right, let's go count that up, make sure that I'm right. So we'll say 1, 2, and I'm going to dot my blocks so I know that I counted them already. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38. So it's about 37.5, more or less. Like I said before, it's just an approximation. Now what we're going to do is kind of outline our area right here. I'm going to choose green for sector 1, just like that. All right. And my distance was 15 blocks here. Just trace over that. And my base was 5 blocks. So we'll just trace that over right there. So this distance is 5 blocks. I'm going to go ahead and shade that in, just so it looks nice. All right, so now I want to map out my second sector. So I'm going to go ahead and write sector 2, and I want this to be my height, that 6 block length height right there in my ellipse. So we know we had about 38 blocks of area before. Like I said, it's an approximation, so we're going to go and about count out 38 blocks and then draw our corresponding line. I've already drawn it because I counted it out ahead of time, but you'll see how it works. Ready? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, and we'll call that 38. Now I'm going to go ahead and trace this out in red pen. This is my second sector. All right. And we know we have an area of about 38 and more or less 38 here. Now what we want to calculate is this distance along here. And in order to do that, just like over here where we kind of counted this length here and assumed it was 5, we're going to calculate this length here and then see how many blocks it actually crosses over. All right, so we'll use our area of a triangle equation again. Area is equal to 1/2 base times height. In this case, that's essentially our triangle, that straight line right there that's going to connect these 2 points, just like that. So my height is going to be 6 blocks. So my area is 38. It's equal to 1/2 times 6 for my height. And then B is going to be my base right there. So 38 is equal to 3 times the base. 38 divided by 3 is about 12.3 or 12.2. All right, so then let's go along the outer edge of this and count up how many blocks we actually have. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's not exact, it's an approximation, but it came pretty close, so we'll say that this is about 12 or 11 blocks. And then I'm going to go and clean it up just a little bit. All right, and then I'm just going to shade it in with pink, hot pink in this case, just very quickly. All right, and you can see that basically what I calculated more or less matches up to what I got. Now in your lab you should have 3 areas like this, so I might pick blue, pick another length here, count out an area of blocks that are equal to the first sector, so 38. So if I were going to do this one, I might draw a line here like this. All right, and then count out 38 blocks just going up and down until I stop, and then draw a corresponding line, just like that. All right, guys, so that is exactly how you do the lab. Once you've gone ahead and done all your calculations, make sure that you color in your sectors, make sure they're labeled. So this should be sector 1, sector 2, and my hypothetical sector 3. All right, let's say in blue. We'll just go ahead and color that in real fast. I didn't calculate this out, but just to show you what it'll look like. Actually got colored pencil to match the lines on my graph paper. That's pretty good. All right, so your end product should look something like that. Now when you go to turn in the lab, there's going to be questions for you to answer, as well as a spot to take a picture of this with all your calculations, everything you assumed. You can write out, if you want to take note of how many blocks you originally picked, the area. Take a picture of this and upload it to the assessment. All right, thanks a lot, guys. Good luck.